Okay, in this video we are continuing our discussion on stresses that occur in beams, and we're going to talk about the other type of stress, and that is shear stress. So again, we're going to use an F to stand for for stress, but this time instead of a B, we are using a V subscript to denote that this is a stress caused by shearing. So this is shear stress. Now the book goes into quite a bit of derivation as to how this formula comes about, but I'll just jump right to the final conclusion of that derivation, and that is that FV, shear stress, in a beam is equal to VQ over IB. So this introduces four variables. What are they? Well, V is the shear force. So again, we did shear and moment diagrams in the last chapter. What we were determining using those diagrams is what is the shear, what is the shear force. So this is going to be in pounds or kips or newtons or kilonewtons or whatever metric prefix you happen to be using. I is the moment of inertia. And you can find formulas for this inside the back cover of the book for some basic shapes like rectangles, circles, semicircles, triangles. For a rectangle, which is the most common shape we deal with, I is equal to 1/12 base times height cubed, 1/12 bh cubed. Now, Q, what is Q equal to? Q actually has to be calculated. It is equal to A times Y bar, where A is the area above or below the location where the stress is being calculated. So that's best explained here with a picture. Let's say we have a cross section that's shaped like a rectangle. Okay, if we go right through its center, that's the neutral axis. If we're wanting to find the shear stress at that location, it doesn't matter whether we're talking about the top or the bottom. Those areas would be the same. If we wanted to find what the shear stress is in the cross section at some other point above the neutral axis, then the area, the A value in that Q formula, is the area above that point. If we were investigating the shear stress below the neutral axis, it would be the area below that point. And Y bar is the distance from the centroid of this area. So this rectangular area we're investigating has its own centroid right in the middle of that rectangle. And then that distance to the neutral axis is the Y bar value. And what else? B, the variable B, is the width of the cross section. So let's put this into practice by taking a look at an example. If we look at example 14.8, we are taking a look at a timber cross section that is rectangular in shape. Its overall height is 12 inches. The width of the cross section B is given to us as 8 inches. And is subjected to a maximum shear force. So they just give us the shear and is equal to 7,000 pounds. We want to first calculate the shear stress at the neutral axis. And in part B, it wants to know the shear stress 2 inches above that point. Part C then asks us to go 4 inches above that point, but I think once we do 2 of these, we'll kind of get the idea here. So let's start at the neutral axis and find what the shear stress is. Shear stress is going to be equal to VQ over IB. Now some of these we can pretty easily plug in. The shear is given to us, that's 7,000 pounds. But what about Q? Q we're going to have to calculate. What about I? I we're also going to have to calculate. B we're just given. B is 8 inches. That's the width of the beam. So let's figure out Q and I. Let's start with I. I, the moment of inertia, and we could also give this an X subscript because that's the I. We're talking about the moment of inertia about the horizontal axis, is equal to 1/12 BH cubed. So that's 1/12 times the width of 8 times the height of 12 cubed. So 1/12 BH cubed, 1/12 8 times 12 to the third should give us 1,152 inches to the fourth. So I can plug that value in here. 1,152 inches to the fourth. Now I need to figure out what Q is. Q is equal to A times Y. So if we're looking at the entire upper half of this beam, we could look at the bottom half, doesn't really matter. One half is the same as the other. Let me change the color here. Let's go with yellow. So we're looking at this yellow half of the beam. If the overall height is 12, then half of that height is 6. So the area is 6 times 8. So 6 times 8. And y bar would be the distance from the centroid of this rectangle to the neutral axis of the beam. So that's basically just half of this height. So it's half of 6 is 3. So 6 times 8 times 3 is 144. And this was in inches times inches times inches. So the units here is inches to the third. So times, that's a parenthesis, 144 inches to the third. All right, so if we calculate 7,000 times 144 divided by 1152 and also divided by 8, we get 109.4. And if we look at our units, we've got 3 inches on top, we've got 4, and this is another one, so we've got 5 on the bottom. 5 minus 3 leaves us 2, so we've got inches squared on the bottom, pounds on top. So as expected, we end up with pounds per square inch, or PSI. So that's the amount of shear stress that's occurring at the center or neutral axis of this beam. Now if we look at part 2, we want to go to part B rather. Part B asks, what if we go 2 inches up from there? So what changes and what remains the same? 7,000 pounds, that's the same. Q, okay, Q is going to be different. What about I? I is the same. and the width 8 is the same. So really the only thing I need to recalculate is Q. So let's switch this color again. Maybe I go with a kind of a purple color. I'm looking at this rectangle. Okay, and it was 6 before, but we've gone 2 inches up from that. So now the height of this rectangle is 4 inches. So the area is 4 times 8. So Q is going to be equal to 4 inches times 8 inches. And now I need to know what Y is, the distance from the centroid of this purple rectangle down to the neutral axis of the beam. Well, the rectangle is 4 inches deep, so I'm coming down 2 inches. And then another 2 inches to the bottom of the purple rectangle, and then another 2 inches to the neutral axis. So it's 2 plus 2 is 4 inches is the Y bar value. So now I've got 4 times 8 times 4, which is 128 inches to the third. So if I recalculate shear stress now, 2 inches above the neutral axis, it's going to equal, I still got 7,000 pounds of shear force. Multiplied this time, instead of Q being 144, now it's 128, so we can see it's a little bit less. And the moment of inertia I is still the same, 1,152 inches to the fourth, multiplied by 8 inches. So if I calculate this, it is now 97.2 psi. So we can see it's going down. It's not as great as it was at the neutral axis. And if we were to do part C of this problem, we would find that it would go down even more. In fact, as we look at, we're looking at a beam from the side, the bending stresses, if you'll recall, are at their maximum at the extreme fibers. We see maximum compression on top, maximum tension on the bottom, at least if it's loaded in the downward direction. What happens with the shear stress is that profile for the shear actually looks something like this. It bows out towards the middle. And while the bending stress is 0 at the neutral axis, the shear stress is actually at its maximum at mid-plane at the neutral axis. So the result of all this basically is that this formula for shear stress, this one right up here that we just used, VQ over IB, we typically don't actually have to use very often, because while this formula can find us the shear stress at any point along the cross section, at the neutral axis or just above it, or a little bit higher, a little bit higher, or a little bit lower, we can basically pick any point along the height of the beam from top to bottom and find out what the shear stress would be. Typically, we're only interested in the maximum value. As an engineer, we just need to make sure that our design is adequate for the worst possible situation, the greatest amount of shear stress. So, having just learned and gone through this formula up here, we can now essentially toss it aside and instead look at some additional formulas for shear stress. But that will wait until the next video.